Uh, we would discuss what is known as the volumetric efficiency of a reciprocating compressor. On your screen, what you see is the pressure volume diagram for a reciprocating compressor, a single stage reciprocating compressor. In this pressure volume diagram, I had plotted four processes: process A to B, process B to C, C to D, and D to A. A to B is the process of compression, where the piston moves from the bottom dead center towards the top dead center. You know that in a reciprocating compressor, the piston would reciprocate between the two dead centers, that is, between the top dead center and bottom dead center, right? And you know that for the compression to happen, the piston should move towards the top dead center from the bottom dead center. So A to B represents the compression phenomena. B to C represents what is known as the delivery of the compressed gas, and for that to happen, the exhaust valve, the delivery valve has to open. So when the delivery valve opens at B, the compressed air is delivered out of the cylinder at constant pressure P2. So if you look at the diagram, you will see that the pressure P2 and P3, they are the same, and that is because the delivery valve is open. C to D, here you find that there is an expansion. And why will that happen? Because the piston would again travel from top dead center towards the bottom dead center. At 3 position or at C position, you will find that there is a space, and that space which is between the top of the piston and the ball heads when the piston is at the top dead center is known as clearance space. Okay, so the clearance space or a clearance volume is necessary, because without the clearance volume there would be no play, or there would be no space for the walls to move. So it is unavoidable to have a clearance volume, and a good machine would have a clearance volume of about 6%, right? So this space which is between the top of the piston and the ball heads is known as the clearance space. In this space is trapped the residual gas, okay, and the residual gas which is at state 3 is in the compressed form. It is at the pressure P2. So when the piston starts moving again uh, from the top dead center towards the bottom dead center, the residual gas would start expanding from position C to position D. So this expansion of the compressed gas occupying the clearance volume, we see again could be assumed to happen polytropically, that is following the law P into V raised to n is equal to constant, and this would continue. Now this would continue means the expansion would continue till the suction pressure P1 is reached. So you see C to D process is of expansion up to the suction pressure P1 from the delivery pressure P2. So P2 to P1 is expansion, right? Now because of that, you would see that the piston has reached position D, and still the suction has not begun. So the suction would begin now at D. So the actual volume taken by the compressor would be from VA minus VD. Okay, why is that so? Because the actual or effective volume sucked in can happen only when the pressure drops from the delivery pressure P2 to the suction pressure P1, right? So this this volume, as you see from the diagram, pressure volume diagram, that is VA minus VD, the effective volume, or V1 minus V4. This volume is less than the swept volume. What is the swept volume there? It is V1 minus V3. So swept volume is more and the effective volume is less, the actual volume is less, and the ratio of the two, that is the actual volume or the effective volume to the swept volume, is known as the volumetric efficiency of the compressor. Okay, so V1 minus V4 upon V1 minus V3, this ratio is known as the volumetric efficiency. So the volumetric efficiency is nothing but the ratio between the actual volume, which is nothing but the free air delivered, upon the swept volume, which is nothing but the theoretical air which the compressor should suck in. Thank you for now.